In today's video, we are going to discuss about the sequential criteria of continuous function. Okay, we all know that continuous function play a very major role in case of real analysis, and we should also remember that a function fx is continuous at the point x equal to a if the limiting value of the function is same as the functional value. Now, what is the sequential criteria of this continuous function? We prefer to say that if a function fx is continuous at a point x equal to a in its domain of definition, then that means this, then we have a sequence xn converging to a for which the sequence corresponding sequence fxn converges to if a. Okay, as simple as that. Whenever we say that a function fx is continuous at a point x equal to a, the sequential criteria says that we have a sequence xn which converges to a, and for this sequence we have a corresponding sequence fxn which converges to if a. Fairly simple, I hope. And if this point a may be taken throughout this domain of definition, that means a function fx which is defined in a closed and bounded interval ab, then we may say that a function f defined on its domain of definition capital X to its range y, if this fx is continuous throughout its domain of definition, which is assumed to be a closed and bounded interval, then for any point x0 in AB, we have limit of fx as x tends to x0 equal to fx0, giving the equivalent sequential criteria as a sequence xn converging to point x0 always gives us a corresponding sequence of values fxn converging to a value fx0. This is sometimes called point-wise convergence. This is a very important concept pointwise convergence. And then we say that this function f is continuous throughout this domain of definition, which we prefer to write as closed and bounded interval AB. Okay, for some specific purpose, we will move on to know in our next videos that what is the implication or repercussion of a function being continuous in a closed and bounded interval. This closed and bounded interval is very important, and therein lies the connection with this sequence. So this sequence takes on values from this closed and bounded interval, isn't it so? Because f is defined on this closed and bounded interval. In this regard, I would like to mention a very important property of mapping or function. What is this? It is that you should remember this is a very, very basic concept, that a function which is defined from x to y, this is a very general concept, and then this x may be any set, but you should remember that this f should be well defined for all the member points of its domain of definition. Otherwise, this f is not well defined. For all x in its domain, we must have a unique fx in y. And we should always remember that for this function to be well defined, we cannot have different images for a unique x. That means this cannot be one to many. Each and every x must have a unique image. No element of this domain set can be mapped or go to different images, but it can be many to one. It cannot be one to many. This we should always remember. And with this definition of function, we should also remember that famous theorem, Schroeder-Bernstein theorem, which says that if we have a function f which is one to one from x to y, as well as a function g defined from y to x, then we say that they are numerically equivalent. That is famous Schroeder-Bernstein theorem. We don't need this function to be 1, 1 and on 2. Whenever this is 1, 1 and on 2, it is obvious that they are numerically equivalent. I have earlier said in my previous video. But if we have a function f which is 1, 1 from x to y, any subset of y, and then a function g which is also 1, 1 from y to any subset of x, then also x and y become numerically equivalent. They have same cardinality. There is the famous Schroeder-Bernstein theorem. I am not going into details of the proof, but the result should be remembered. Now let us discuss something about the Bolzano-Weierstrass property. Bolzano-Weierstrass theorem, which states that every bounded sequence has a convergent subsequence. Every bounded sequence has a convergent subsequence. So this very statement of this theorem gives us the importance of defining a closed and bounded interval AB, isn't it so? Since this sequence is bounded, we can say that Xn is a sequence which is contained in this AB, because for all n we have the values of Xn bounded by these two values. One is the lower bound and other is the upper bound. And we should be aware of the fact that the real line R has a completeness property, which states that if a set in R is bounded, then it must have a supremum which is least upper bound and an infimum which is greatest lower bound, GLB and LUB. It's quite conceivable that whenever a set is bounded, we may think that a set of values is bounded means it has a upper bound as well as a lower bound. Now what is the meaning of this statement? We have a set of values, say a sequence of values Xn. This has a upper bound, say capital B, and a lower bound, say capital A. So all the values of Xn is greater than A and is less than B. Now one can easily say that 2B is another upper bound while A by 2 is another lower bound, isn't it so? So what we are really interested is a value, say B prime, which is such that it is the least upper bound, and similarly we have a value A prime which is called greatest lower bound. That means this is the greatest value which will be the lower bound of this sequence. If we increase this value by even slightest amount, this will not be the lower bound. We will have some members of Xn such that which is not greater than this A prime plus epsilon. Okay, this element will be less than A prime plus epsilon, and whenever this member will be less than A prime plus epsilon, this will guarantee that A prime plus epsilon is not the lower bound. Similarly, this is the least upper bound, meaning that if we reduce this by even the slightest amount epsilon, positive amount, but very small, arbitrary small, however small one can imagine, then B prime minus epsilon will not remain the upper bound of this set, meaning we have at least some Xn0 prime which is greater than this. So it will not remain the upper bound. So these two values are very important, isn't it so? We should remember that. The concept of supremum and infimum, greatest lower bound and least upper bound. Now with this concept, we move on to give another idea of what we say nested interval theorem. Now what is nested interval? We can assume that this is AB Okay, so A is the lower bound and B is the upper bound, and we may imagine a sequence of values a1, a2, a3 dot 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 an plus 1, and b1, b2, b3 dot 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 bn plus 1, such that these values are monotonic. We always should remember that A is less than B. This is a real line, and for the sake of simplicity we may as well take it to be the positive part of the real line, plus infinity. There is no loss of generality, because we all know that all the features of this positive real line is same in the reflection of the left hand side of the real line. We can put a minus here and we have the reflection of this point with respect to this origin. So there is no loss of generality in assuming that A and B both are positive, and A is the lower bound, B is the upper bound, means that A is less than B. And all these points A1, A2, A3, since this real line is ordered, they are situated like this. Okay, so A1 is less than A2, A2 is greater, this is A1 and this is A2, similarly A3. So this is monotonic increasing. And what about this? In case of B, we assume this to be B1 and then this to be B2. This was A1 and this was A2. So obviously this B1 will be greater than B2, and this B1, this B rather, will be greater than B1. B1 is less than B, B2 is less than B1, and so on. Isn't it so? So this is a monotonic increasing and this is a monotonic decreasing subsequence of values of this interval. All these two sequences, these are two sequences, isn't it so? And we have A1 comma B1, then A2 comma B2, then A3 comma B3. All right, we can write it as I1, then I2, then I3, then IN plus 1. We can easily conceive from the picture the concept of this nested interval, and we all can infer that this I contains I1 and I1 is contained, I2 is contained in I1 rather, I3 is contained in I2. They are reducing. And if we go on doing this, since these two are monotonic and bounded, so they will converge, they will be convergent from the properties of a sequence of numbers. It is very easy to prove. And from this, we can easily infer that the basic idea of Bolzano-Weierstrass theorem is proved, because this is a bounded interval. So we have a sequence xn which lies in this, and we can easily show that this has two convergent subsequences. Okay, so let us take a very quick look at what we perceive about the boundedness and monotonicity and convergence of a sequence of numbers. Okay, let us take a quick look. This is a sequence of numbers where n is the set of natural numbers. Okay, it may be like this, it may be like this, it may be like this, it may be like this. This is sine of 1 by n, and this is e to the power n. Okay, one may write this as sine of 1 by x also, and then express this x in terms of n. This is a very special function, sine of 1 by x. Just imagine that we can replace this x with an expression like this. Or we may anyway, these are different examples of a sequence. Now, what is the concept of convergence of this sequence? Convergence of this sequence xn to a specific value L means this for all n larger than a prefixed large number capital M. This M is arbitrarily large and then epsilon, this epsilon is arbitrarily small. The meaning of this line is that after a particular value of this natural number, all the values of the members of the sequence of numbers gets closer to L, or we may write like this, that xn is in epsilon neighborhood of L for all n prime which are greater than a prefixed large m. Isn't it so? So, whenever a sequence is convergent, it must be bounded, because bounded means this for all n. And from here we can easily infer that whenever a sequence is convergent, then we have it to be bounded. But it may be a bounded sequence which is not convergent. The simplest example is that if we take the example of, say, -1 to the power n by n. Why? Because they will differ by sign, and whenever they differ by sign, we cannot make it arbitrarily close. If we wipe this out and write this as a sequence, this is also a very special sequence which has only two members but which do not converge, and it has two different subsequents which converge to different limits. -1 is convergent to -1, and +1 is convergent to +1. They converge to two different limits. So whenever a sequence has two subsequences which converge to two different limits, the whole of the sequence is not convergent. This is quite conceivable, because we cannot make the difference arbitrarily small. The difference is always 2 mod value of any two subsequent members of xn, isn't it so? Now let us go back to the concept of continuous function and its sequential criteria. I would like to mention here the different type of discontinuity. of a function. Let us recapitulate it. One is when limit of fx as x tends to a does not exist. Then we cannot think of continuity at x equal to a, isn't it so? Because the very basic definition of continuity at x equal to a requires that the functional value will be equal to the limiting value. Whenever x tends to a, the limit of fx will be the value of the fx at x equal to a. So whenever this limit does not exist, no question of continuity arises, and this is called non-removable discontinuity. Okay? Non-removable discontinuity. But whenever this limit exists and is not equal to fa, then we have the second type of discontinuity, which is removable discontinuity. Because the limit exists, but it is not equal to the functional value. Why it is removable? Because we can define the value of the function forcefully to be fa. We can adjust it. That is the basic idea. Okay? So now let us get back to the concept